should we do the protein structure? Should we talk first about the exam? We can talk about the exam after this thing. Okay, so let's start with protein structure. So you start the video?
Yeah.
Okay. So of course you know macromolecular structure connects sequence to function and is the basis of recognition. And the reason, I mean, it's kind of important in bioinformatics to keep remembering structures because we can't think of, again, biological systems as being like a computer. If a computer worked the way a cell works, you would probably want all new parts because it makes mistakes, and because how it reads things and how it writes things depend on what exactly it is that's being written, and it's interacting in this big soup. So all that is important. Let's see. So we're going to talk about the building blocks of proteins, side chains and how they interact with each other, secondary structure, and a bit about domains and how they aggregate to form multi-domain quaternary structures. So most of this I think is going to be a review for you guys. If everybody knows the core rule, how to distinguish between L form, which is dominant, and R form of amino acids. And so basically the way you look at what we're looking at here is we're looking at the alpha carbon, which is this one with the red, with the green sphere, which represents the side chain. We're going to look down the hydrogen at it, and what we should see is that the carboxyl carbon, the R, which is the side chain, and the nitrogen, and they should be going clockwise. And if they're going anti-clockwise, then we have the R form. Let's see. So we talked. We've already talked quite a bit about structure and how it's how we should be able to rationalize which residues are likely to substitute for each other in evolution. Right. We said, for instance, that if we have valine, a beta branch like this would be very similar to, for example, isoleucine. Right. So isoleucine just has this additional methyl group, so for sure an increase in volume, but otherwise relatively similar. And so again, we expect a high score in the substitution matrix for this transition. And then we also expect things to stay within their physical chemical class. So for instance, this transition from lysine to arginine, that's something that can often happen. It's an increase in volume, but it conserves charge. And then likewise, going from aspartate to glutamate, that conserves charge, conserves the opposite charge, negative charge. And then we can also do things like go from aspartate to asparagine, right? So perhaps you can see that the structure is highly conserved, but the problem is that we've now lost charge, right? So that's a big deal. But maybe this transition will be easier to do than some others, right? For example, going this way would be even harder. So do people more or less know the physical chemical classes of nucleic acid? Amino acids. For example, if I just say phenylalanine off the top of your head, what class is it? Right.
Alcohol aromatic.
Yes. Yeah, and there's some that are special, right? So, for example, proline, that has a special kink, or chooses a special kink into the backbone, and so that's something that doesn't really substitute very well. Likewise, cysteine, that tends to be in disulfide bridges with another cysteine, so changing that to anything else is kind of a big deal. So we should have some concept of what's happening in terms of physical chemistry between, for example, between these interactions between side chains. And one thing that we keep talking about all the time is our hydrogen bonds, right? And so can anybody tell me what's the driving force of a hydrogen bond? Why does this hydrogen want to be near this oxygen, for instance, in water? You know? Yeah. Sorry? Yes, exactly. So what happens is that oxygen is electronegative, so it likes to suck up the electrons from these hydrogens, and so these are net impoverished in electrons, and so the nucleus is more exposed, so this looks like a partial positive charge. Like meanwhile, the oxygen looks like a partial negative charge, and so you have a direct monopole interaction between these plus and minus, but then you also have the dipole interaction because of course you have a net dipole involved. There's also the ultrastatic interaction. So for example, in a salt bridge, you see let's say a negative charged glutamate with a positively charged lysine. You can get this QQ over R interaction. And then there's a van der Waals interaction. And so a van der Waals is an induced dipole interaction, meaning that you can think of it as the electron cloud being displaced such that it makes a dipole-dipole interaction between two atoms. But it's not quite as simple as this because it really can't happen like this. It has to happen as a superposition state. So you have basically, both clouds shifted one way and both clouds shifted the other way, and it's actually in these two states simultaneously in a sense. It's not an interaction that can be explained classically. Okay, and then there's the aromatic interaction. So most of the time we're going to see this sort of offset stacking. And so what we're looking at here is usually we're talking about some cyclic group, which is going to be enriched in electrons in the middle. You might have a pi orbital above and below, and what these electrons want to do is they're going to interact with something that's impoverished in electrons, in other words, has partial positive charge, and it's going to find that along the outside of these rings, right? All these hydrogens on the outside are going to be net partial positive charge. And so that's why you get this sort of offset. And then you can also get this T interaction where, for the same reasons, you've got this edge which has a partial positive charge interacting with a net negative charge above and below the plane. Okay, and sorry about these slides. My laptop died over the weekend, so I'm making do with these two crappy computers. And I can't fix this right now. But anyway, this is the backbone of an amino of a peptide, and so you're going to typically read from N to C. So N this way, and so we call this phi and we call this psi. And let's see, do I have the convention? But I guess you guys know that the convention is such that if you have 4 atoms, let's say A, B, C, and D, the convention is that you're going to look down this middle bond. This is your eyeball here. And let's say it's like you're grabbing this middle bond, and your thumb is pointing away from you, and so this the extent to which A and B are not aligned is your is your torsion angle, right? So right here we've got 0 torsion angle, but as it starts to rotate sort of out of the board this way, then this grows. It goes to 0, and over here it'll be 180, and so on. And so there are certain preferred values for these phi and psi. Yes.
Can you explain that again? The angle.
This one? This?
Yeah,
oh,
the
that.
angle,
Yeah,
what
sorry.
you do.
Yeah. So, what's your background, if I may ask?
Chemical.
Chemical engineering. Okay. So, so basically, what's the easiest way to do this? So this is pretty good. Let's say we're interested in this middle bond. And what we're going to do is we're going to look, this is A, B, C, and D. Right? Just pick 4 atoms and use that. And so if you're looking down this middle bond, then A to D, if they're lined up, that's 0. And they start to rotate this way, like right-hand rule, so you go like this. And that's like 10 degrees, 45 degrees, 90 degrees.
So the angle between the A and D.
Yes. Yes. Okay, so back in the day, well, first of all, does anybody know how Ramachandran developed the Ramachandran plot? Back in the day. No one? Want to guess? It's basically was something like this. I don't know if he actually built it or if he just worked it out on paper, but it was basically hard sphere approximation. And so what he did is so he looked at different values of phi and psi. And again, remember, we said this is phi before the alpha carbon, and this is psi after the alpha carbon. And so you can see there's certain values that just don't work, right? So for example, this thing, the carboxyl oxygens right next to each other, this is not, they're not going to be happy, right? Even if it's not, prohibited by their van der Waals radii, they have similar partial charges, and so nothing like this is going to be stable, right? And so this happens when you have, what does that look like to you for a torsion bond? Like what's the torsion angle here? A, B, C, D. Go ahead. 0, yes, exactly. So phi of 0 and psi, something like, I think I remember it being 120. Although here it looks like minus 120. But anyway, there's some, we'll get to that slide in a second. But anyway, there's a psi angle which ends up putting these two together. And sure enough, there's actually a whole region, basically anything with psi equals 0, it's not going to be happy with, right? M psi 120, it's one of these regions that was not allowed. So these are regions that are allowed, right? Oops, alpha helix and beta sheets. And so that's one thing that's not allowed, is these carboxyl oxygens next to each other. Anybody know what else is not kosher, not permitted, very much forbidden? So if we get this side chain next to the carboxyl oxygen, does that look happy? Not terribly, right? So this happens at looks like 120 for phi, and I think it doesn't matter what you have for psi. I have another slide that has that. Nice image. But anyway, there are certain angles that, or entire ranges of angles that are not allowed, right? And surprisingly, this turned out to be, like, considering that this is a very crude approximation of what a real molecule is doing, it was actually really impressive in terms of how well it is able to predict the later statistical compilations that observe phi and psi. Right? You can see that these guys align actually quite well with those gray regions up there. Any questions? So far we've got a couple of constraints. We've got the chirality, which we said is mostly going to be L-form, almost predominantly L-form. And we talked about some forbidden regions of the Ramachandran plot. And then of course we have the chemistry, like it's always going to be N carbon, nitrogen carbon, carboxyl carbon, another nitrogen, and so on. And the alpha carbon is going to have the side chain. And so it turns out that these, you add up all these constraints that you have, there's actually not as many conformations that are available to a polypeptide, right? And so this tends to restrict the physically stable structures that's going to form, right? And so we end up getting these structural motifs that occur again and again, right? And so for example, we have beta sheets. So beta sheets are interacting with each other by hydrogen bond across strands, and what you're looking at is a hydrogen bonding interaction between this carboxyl oxygen and this amide nitrogen, and these are going to line up actually really nicely. In the case of this anti-parallel strand, we've got, you can see here, you got carboxyl oxygen interacting with hydrogen, the amide hydrogen. And then over here it reverses, and now you've got the hydrogen on the bottom strand interacting with the oxygen on the top strand. And so it repeats. When you have that, so that's the case of anti-parallel, meaning one going this way and one going that way. When you have parallel, you still get hydrogen bonding, but it's a little bit different. It looks like it's going at a little bit of a slant here, and it's still between the carboxyl oxygen and this amide hydrogen. And now it reverses, and now it's oxygen to hydrogen, and so on. Which of these two is more stable? Parallel or anti-parallel? Why?
There's more number of hydrogen bonds in the anti-parallel strands, and they're also more stable because the bonds seem to be parallel to each other compared to when in the parallel strands.
Yeah.
Where there's an angle with which there's the bonding that
Yeah,
occurs with hydrogen bonds.
So in terms of the number, they're probably the same, but yeah, you're definitely more straight. You've got greater distance, and I'm actually not sure about whether angularly it's ideal. But anyway, you certainly have more distance between hydrogen bond donor and acceptor. Okay, so exactly right. Let's see. So do you see a pattern in the side chains? What are the side chains doing as you go, let's say, along the strand from N to C? Anybody see what they're doing? I think you're doing the right thing with your fingers. Go ahead.
It's just a visual representation, so they're alternating in such a
They're
way that
alternating,
they're not on the same
exactly.
side for steric impulse.
Exactly. So you can see, let's see, R. Yeah. So the convention here is that if the bond is like thick and thin, the thick side is towards you, right? And so the side chain here is towards you, and here it's away from you, and here it's away from you also, and towards you and away from you, right? So, is there a reason why it has to be that way? You want to tell me the reason why it has to be that way? Is there a reason? Go ahead.
The color, because all the amino acids are in L conformation.
Yes,
And
yes,
if
exactly.
you want to form the peptide bond, they have to be that.
Yeah, exactly. So they're all in the same peptide, they're all in the same chiral state. And then, so if you have one going up like this, and if you look at the backbone, it's basically doing 180 degrees every time. Like all these torsion angles, well, they're not exactly 180 degrees. So this cartoon, they're 180 degrees. Close enough to 180 for these purposes. So the point is that if you have this and then it rotates 180, rotates 180, rotates 180, between this R and this R, there are 3 torsion bonds. They're each doing a half turn. So you end up doing a half turn every time you go, right? So if you go up like this, you do a half turn, you're going to end up down. You do another half turn, you're going to end up again, and so on. Okay, very good. Okay, and then we have alpha helices. And does anybody remember what the periodicity is of an alpha helix? I don't think I have it on the slide. Like, we again have hydrogen bonding, right? Here's this oxygen interacting with an amide hydrogen up here. Maybe this is a better example here. Oxygen to hydrogen. So the numbering of this, let's say this is I. What would this be? I plus. Can you hear you? Is that you? No? 4. 4, exactly. So the periodicity is I plus 4. So all these are interacting with a residue, 4 residues ahead. And what can you see regarding the orientation of these carboxyl oxygens?
Maybe I'll point to the C terminal.
Exactly. They all pointing towards the C terminus. So if you see these oxygens, they're all pointing in the same direction, N to C. If you don't see which direction it's going, just remember it's always N to C. So here you've got N, alpha carbon, carboxyl carbon. So it's going in that direction. Okay. And so what does that end up doing for us electrically? Dipole, exactly. So there's a net dipole because you've got a negative charge here and a net positive charge here, and they're all going in the same direction. So all these little dipoles are becoming a big dipole. Okay. So some of you might have seen this before. How many of you have seen this before? Okay. Yeah, 1 or 2. Okay. So what are we looking at? So we said that there's an interaction between residues I and I plus 4, right? And so that means if you think of this, these side chains being kind of these knobby things that are sticking out of the helix, there's going to be knobs kind of like going every 4th residue, and they're about as close together as you can get, but they're not quite linear, right? They're because they're not exactly four residues per turn. It's a little bit less, and so you end up overshooting. It's more than 360 degrees between these two guys, right? And so if you line up along these knobs, it makes like a screw thread going along the outside of the helix, except with a much higher pitch than the backbone, right? And so it's like, you know, if you were trying to, basically, if this were a screw and you're trying to screw it to a piece of wood, every turn it would go way up into the wood. And so basically, this is one thread, and then you have another thread here, and you know, one basically going around like that. And so the closest one is the closest distance is between I and I plus 4, but I and I plus 3 are not that far away either. So you can also think, okay, well there's all these knobs on the outside of this helix, but if I go this way, there's also some knobs relatively close this way. So I can also think that there's sort of like a screw thread going in the opposite direction, except with not quite as much pitch, right? Like this. And these have a characteristic angle with respect to the axis. And so here, this one, which is the I and I plus 4 one, is 25 degrees from the chemical axis, and then this one, which is between I and I plus 3, that's 40 to 45 degrees, and it's left-handed. So it's the opposite hand of this. And the reason I'm harping so much on this is because if you get two basically wooden dowels, just cylinders, and you put them next to each other, they can be perfectly parallel, right? But what happens if you take threaded rods, like basically screws, and you put them next to each other, and you press them together as hard as you can? Do they want to stay like this? No. I mean, like the threads have crest and trough, and you're going to want to stick into each other like that, right? So you're going to end up getting a preferred interhelical angle. And so that's what alpha helices do. If you have two of them, one way they can fit together is they can stack like this. And the way you want to think about this is that on the front side towards you, it might be going off to the right like this, but then it goes around the helix, and on the back side it's going the opposite way, right? It's going like this, and on the back side it goes like that, right? And so on the back side it looks like this, like the left. I just shift this to the left. And so the way you're going to stack these up is that you're going to have to rotate this one 25 degrees just to get it to where these threads are vertical, and another 25 degrees so they align with these threads, right? And so you have to get 25 plus 25, and that ends up giving you interhelical angle of 50. Yeah. And so that's why if you see proteins that are rich in alpha helices, a lot of them will have helices that are 50 degrees. Right? It ends up not looking quite so aesthetically pleasing as this case. Well, I think we have examples of both in these slides. But anyway, in this case, you've got interaction between this I plus 4 threads and these I and I plus 3 threads. Remember, this is the front view. So that view of this guy has them going this way, 45 degrees. And we want them to lie in here. And so all we have to do is go from 45 degrees a little bit up to 20 degrees. Right? So we just shift this 20 degrees to the left, and now it's going to sit right here. Right? And so you do that, and you get this 20 degree helix. And this looks a lot more symmetric. Like, for example, human growth hormone has this. And so you look a lot more neat and organized. This one looks a little bit more chaotic. So that's the explanation for interhelical angles. I wouldn't worry about I plus 3 and I plus 5 helices. There's these beta turns, and these have very tightly defined reason for having these geometries. Like you have to have a glycine in a certain position to make it happen, and so on. Like this. So yeah, here are these two examples of beta turns. Here's this hydrogen bond, selenium bond that you have, and there's two variants depending on whether you have how many residues you have in the turn right here. And you have an interaction between n and n plus 2 or n and n plus 3. Okay, well, here's the image I was telling you about. So, yeah. So we said that if we do, let's see, phi equals to 0, so that would be like this. Phi equals to 0, and psi equal to 180. You end up like this, and you get the two oxygens right next to each other. And you can maybe play with that and convince yourself that it's true, or maybe not true. Do you know what this one, or do you have enough out there? All right. So now just a little bit more zoology, basically. So this is a beta tern, or a hairpin, sorry. And you can have these hairpins stacked up basically forever, right? It becomes a beta sheet, or beta meander in this case. And these can be open, or they can close on themselves. And this makes, for example, a tin barrel. They can also, I didn't go into this, but they basically have the sheets in their most sort of physically favorable configuration, or not flat sheets. They have a net sort of twist to them, and so if you stack them up, they can make something that looks like this. It's called a propeller, and this can have any number of blades between 4, 5, 6, 7, and 8, and so on. This is a Greek key. Who here's from Greece? Yes. Can you tell us why it's called a Greek key? Yeah, I mean, it took me a long time to figure this out. Okay. So, why not a Mexican key, or I don't know, Thai key or something? So, finally, I figured out. Have you ever seen this? Yes. Right. I mean, everywhere basically. The Greeks just love this motif. I mean, it's a nice little motif. I'm not saying it's a bad motif, but anyway, this is basically it, as far as I know. It kind of looks like that. Nothing more than that. Okay, and so you can also have something called a jelly roll. It actually, you can only see, it really only looks like a jelly roll when you look at it as a cartoon like this. If you look at the actual protein with atoms, then it's really hard to see it looking like a jelly roll. But anyway, a jelly roll just means that you have these two layers, or this anti-parallel beta sheet, and you can just sort of roll it up, right? It has to do with the topology, right? That's why you call it beta sheet, jelly roll, and not, let's say, a beta meander. So we've seen mostly anti-parallel sheets, and of course that's probably because they're more stable. But they can also have anti-parallels, and so this is, for example, an anti-parallel beta sheet that's made of a triangular prism. I'm sorry, I should have actually used the other computer, which did a little bit better job with the Greek letters. But this is beta, alpha, beta, right? And that just means there's a beta, there's an alpha, and there's a beta. What do you think this angle is? I can see you thinking, the two of you. Spit it out. No, I mean, in a good way. What do you think this angle is? Just guess. What's your guess? That's my guess. Yes. So basically, why?
It looks very similar to the previous diagram.
Yeah, I actually haven't checked this, but I think it's got to be these residues from the I+4 interaction lining up. So this is a Rossmann fold. So just beta, alpha, beta. Actually, more like beta, alpha, beta, alpha, beta. Two of those. They can form a tin barrel. Here's the helix bundles I was telling you about. So here are the 20-degree apart ones. And so you can see they're, at least I find them a little more symmetric looking. And here's 50 degrees, right? And so it's more chaotic. And so I think this is the first protein crystallized. And people made derogatory comments about its aesthetics. Okay, so there's this concept of a domain, and a structural domain is basically a folding unit of a protein. And so basically, there's some debate as to what the definition of a domain is, but for me, a domain is a fragment of a protein that would be stable in solution, right? So if we were to cut this here and here and separate these two fragments, each of them are probably soluble and stable, right? Because they might each have their own hydrophobic core, so they can fold on their own. I've actually worked a lot on hinge predictors, and one way you can predict hinges is by cutting these and then calculating their stability. And it turns out that if you made the cut in exactly the right spot, then the stability is much higher. It has very low p-value. It's an excellent way to predict hinges. This is domain swapping, so this means that you can have A interacting with B, but maybe B can just as easily interact with an A of another residue. And then this has consequences sometimes for things like amyloids and so on. Domains can have different evolutionary origins, so they can be the results of a gene fusion. Let's see. So the proteins can also make quaternary structure, meaning that two separate chains can come together and make a dimer. 3 can come in, make a trimer. 4 can come in, make a tetramer, and so on. I don't know why we went with Greek numbering here and not Latin, but we did. That is Greek, right? Tetra is Greek. Okay. Okay, and this sort of multimerization can be globular or fibrous. If it's globular, it's probably defined multimerization, like in terms of it's always going to be a tetramer, or at least there's a maximum number. But for these fibrous ones, it means that multimerization can continue more or less forever. This is an example of convergence versus divergence. So these are two different proteases, and they have the same catalytic triad, but everything else that's outside of it is completely different, right? So probably different evolutionary origin, but they both evolved to do the same job. So convergence at the molecular level. And so you've learned a lot of folds, and it turns out that if you have the same fold in two different proteins, it's not really clear that they came from the same they have a common ancestor, right? I mean, there are very many cases where there's absolutely no sequence identity, and maybe you'll never be able to prove, or at least not to my knowledge, it hasn't been proven that they don't have a common ancestor. But to me, it seems likely that given all these different constraints, the same fold could have been rediscovered many, many times in evolution, right? So for example, beta alpha betas, those might be just so stable and so energetically favorable that even if some organism were to completely forget beta alpha betas, it would probably reinvent them again some number of hundreds, thousands, or millions of years later. So these are examples of ways that proteins can oligomerize. I don't believe this one. I don't think it's mathematically possible to have a perfect linear oligomerization like that. It has to have at least a little bit of spiral character. More multimers. Another example of, well, same example of metamerization. That's it. That's all I have for you on protein structure. Any questions? Any questions at all? Yes.
It's actually not about the content, but could you upload the slideshow where the pictures are not about the text on like the last 10 slides so we can read the text? Like the one before? Another one? Okay. Yeah, that one, for example. I don't know if the text is important, but
it doesn't look like it's that important, but yeah, I mean, if it was important enough to write, it's probably not important enough to erase. So I'll go ahead and erase it, or move it down if I think it actually adds something. There's another example, and another. Yeah, I mean the things like I've switched back and forth in Keynote and PowerPoint several times, and each time something gets lost. It's okay. Sure. The only issue is that, like I say, right now I'm in this crappy zone where, like, I have Windows on my left and iPad on my right, and no reasonable personal computer. Right? It's just in a very bad place right now. I was building my daughter's treehouse, and I put down my laptop, and then I thought it'll be safe from the rain under this cover, not noticing there's actually a puddle under the thing. Yeah, I didn't even try to claim that it was under warranty because I already know it's gonna be like water intrusion markers all over the place. Anyway, so that'll take up to 2 weeks, but I'll try to fix it. Let's see how much time we have. There are a couple of luxuries that we can engage in. Oh, first of all, are there any other questions? Yes,
Maybe a question further on convergence versus convergence, depending on just protein structure. Like how many percent of the protein structure should be similar so that you actually conclude that there's.
I mean, I don't think there's a straight answer for that. You always conclude that they have a common ancestor. Well, yeah, I'm sorry, I don't think I have a straight answer for that because even if they were perfectly, very, very similar, like, let's say completely different sequence but exactly the same structure, like let's say the beta alpha beta, that's an example. How do you know? Just because they're so similar, that doesn't mean that they had a common ancestor, right? I mean, all you know is that they obey the same physics, right? They live on the same universe, basically. So, no straight answer. But in general, people say that if it does the same, like it does different things, but looks very similar, then that's an example of, I mean, if it's big enough, like sometimes so big that you say, oh, well, yeah, they have to have a common ancestor. I don't know if you know what I said, but anyway, so if it looks very similar, even if it has a different sequence and doing different tasks, it's possible or maybe even likely that it's divergent evolution. Whereas if it does exactly the same thing but has no structural similarities, more likely it's convergent evolution. Other questions? So the luxuries that we can engage in now are, we can look at the exam. We can do this. This is the neighbor joining exercise. I figured out why it's just like you just have to have a special technique for making sure they meet up in the center. I think you probably want the exam more ardently. No? You want to do this? Okay, fine. Somebody come up. 3 people. And can I have like 3 volunteers? And so as you recall, we had these 3 sequences, A, B, C, and their evolutionary distances were 4. Let me just make sure I put it in the right order. 4, 3, and 2. Do you want to do this or you guys just want to go home? Oh, okay. So Jana and you 2 guys. You 2 the lower line. Sorry, that guy. I lived in California for like years, so I call everybody guys, even women. Sorry. Let's see.
You guys said it.
I know it's bad. Here, can you sit here, John? And two ladies. Hold these two together like this. One is here. That's 2 meters, 3 meters, and 4 meters. And actually, the trick is further tighten. Three, 4, okay, that's fine. And this is 3 meters, and this is 2 meters. And I guess your job can be, I'm making note myself. Keep it tight. Yeah. Okay. So what is the distance between I and C? And you are P, is that right? Yes. So what is the distance between first of all, what is this distance? How long is that? Let's guess. Each knot is 1 meter. From here, the common ancestor to there, how long is it? So from there to here, it's 1 meter. From here to here, it's half. Yeah, of course. I mean, this is not going to have precision in the calculation, but yeah, you're saying 1.5. And that's, you said you're, what's your name? Maria, and you're B? Maria? And so this is from B to the common ancestor series is 1.5. That's called little b. Now, is that right? No, it's this is.
Do you want me to hold it?
No, you're actually A. No, I'm C. And John and I is C. So that 1.5 is actually little a. And that's actually the same number I come up with in class. No one's convinced by this, are they? Maybe it would have more impact if we did the math and the demonstration at the same time. But anyway, thank you. Do you want to look at the exam now, or you just want to go home? Exam? All right. Let's see if this works. So, yeah, there's some problems with the last few questions that I have to discuss with Arnav. He has to decide how he's going to grade those. But anyway, so here's this first one. Looks like most people got it. Any questions about this one? We did this in class, so it shouldn't be too hard. At least after the fact, it shouldn't be hard. Yeah, this was a little bit problematic. First of all, people know why you can't use the poly-A signal to improve the prediction of genes in prokaryotes. It doesn't exist in prokaryotes, right? Yeah. I mean, so maybe you look for promoters or something, but not poly-A. And the other one was I'm a little bit reluctant to go through the math, but because there's two different mistakes in it. But the point is that there's some probability of finding some start codon, right? And then as someone pointed out, there's actually 3 start codons in prokaryotes. So let's see, GUG, what's the third one? You guys remember? Anyway, some other.
AGA, right?
Sorry?
Isn't it AGA?
AGA. I'll just go with that.
I don't remember.
what are the odds of finding a start codon if all the residues are random? Like at a given position, what are the odds? First of all, how many possible three combinations of 3 amino acids are there? No? Like, I'm sorry, that's amino acids, I meant nucleic acids. 4 to the what? 4 to the 3, exactly. 4 to the 3 possibilities. So that's 64. And so the odds of finding the start codon, assuming randomness, is what? And then these are the odds that at any given position is the beginning of a start codon, right? And then you have some number of bases, and that was for a million or something. Is that right? Is it a million? Yeah. So this gives you the number of start codons. And you're only reading in one sense, which is probably debatable. But anyway, you're reading in one sense only. And so this should give you the total number of start codons, assuming these are all random. And then you're asked, what's the probability that the next 50 codons don't contain a stop codon? Right? Let's see, how many stop codons? Right?
3 stop codons, so the rest is 61 out of 64.
3 stop codons. And so what's the odds of the next codon being a stop codon? No, it's actually more to the point. What are the odds that it's not a stop codon?
And 61 out of 64.
61 out of 64, exactly. 61 out of 64. And what's the odds that 50 codons are not stop codons?
The power of
Exactly. So of the start codons, of the start points of genes, the ones that get all the way to 50 codons without hitting a stop codon is this number. Right? And then he computed it for me, like it was 1,000 or 4,000, something like that. Yes.
I don't know if someone can correct me, but I don't remember someone explaining that to us before.
Someone? Or
Someone explaining this to us before.
You know what? I really can't.
It makes sense now that you say it,
Yeah.
but no one said it before. So
I mean, I like I have talked to Arne, but I think we're just gonna we just have to get over the point because it's not just this, but also like there were 3 codons and not one. Yes.
But the main question I have with this is that the formula we got shown in the exam is not the formula we just see on the board.
Yeah, on the exam this was a 1, right?
Yeah.
That was the other problem.
And then it also said that it is
Or
50
the
or 50 base, like in a range of 50 base pairs or longer. So that was
50 amino acids, right? 50 codons.
it's actually genes of a length 50 or longer can be estimated.
I think they meant 50 amino acids.
Yeah, so it's
So it
not-
doesn't say, is that what you're saying? It's unclear, or you thought maybe it was 50 nucleic acids?
but also like the difference between 50
So I mean,
or
it would have
longer.
been a little bit better to have this be like, have some constant up front, right? And then you could any of those would be fine. I'm sorry, I did look at his questions and they looked okay, but then I didn't think of these issues. And I don't think I can take responsibility for his questions, but I'll talk to him about it and see what we do. So, yes, in fact.
Maybe unrelated question. In Canvas, one of the pre-lecture quizzes was marked as given late. So the due date was changed to 13th of January, which was actually before the course started. So it's now marked as if we would have handed it in late.
But you got a grade, right?
Yeah, we just wanted to ask if that will
No,
have an
it's not
impact
gonna.
on-
There's no weight given to lateness. like the way we handle it is like it cuts off if you're late, if you're really late, and then you can't do the quiz. But if it's marked late, it won't affect your grade. Let's see. So let's just go quickly and do. Let's see. Number of genes in the human genome before the first. So looks like most people got this anyway. It's a bit of memorization, but anyway. Phylogeny, advantage of neighbor joining compared to EPGMA. Most people got this. That was actually really good. Yeah. So this one has to be regraded because some people didn't select 15, but it was the right answer was changed after the fact. But actually, there's an additional right answer because it doesn't actually say UPGMA, so it could be. I think we figured it could be 24.
I think the problem is that we typed 15 and not 15.00.
Yeah.
It's gonna. I doubt that, but
And it's like typed 15 and
no, because the thing is that the right answer before you took the exam, the right answer was 12, which is actually incorrect, right? So that's why I got marked wrong.
okay, but it's
So-
still marked wrong.
It's still marked wrong. It still has to be fixed. I still have to go and harass Art. Let's see. Machine learning. Okay, people got this. People knew which one's a sigmoid, which one's a hyperbolic tangent, and which one's a ReLU function. And then people got this right. And then there's a free text answer which hasn't been graded yet. What do most people think it is? Yeah, I mean basically this is probably right because it's very like for sure this is wrong because it's just overfitting. Like these could be just outliers, and so next time you try it on a new data set, they're unlikely to be in the same place. Anyway, so that has to be graded manually. Yes, in the back.
Yeah, how would we know that it's overfitting if we don't actually know what the model
That's a
is
good question.
about? Because, like, I mean, when you have 20 neurons, that's 20 sets of different things that are happening every single time. You know, right?
Yeah.
So
let's hope if you actually wrote that in your test that he was taking into account. I think he did say something in this particular case, like he put his figure and talked about overfitting. So I feel like if you went with this one, I mean the point you're making could be correct, but it would also indicate that you. I mean, if you were listening to his lecture, you would have ruled out at least this one. Like I said, I can see that there's some room for debate on that point.
I mean, yeah, I know he used that in lecture as an example, but like the mathematics behind it don't necessarily you don't back that up if you think about like what it is that goes into creating the models.
He didn't say anything about the underlying system, right? So maybe you're right. Maybe it's a very complicated system that happens to look like this. It's possible. I mean, with such so little data, I really feel like most people would rule this out because when your solution is more complex than the data itself. Like look at how the number of points and look at how many parameters you have here. It's like the potential for overfitting is very large.
The only reason I'm saying it is because there's also a lot like in the reading about how to like define a function using a neural network, and if like for example you were creating if you wanted it to represent some sort of function, like, there's no reason that it couldn't be the one on the right being.
There's no reason it couldn't be, but with such a small amount of data, you really would have a hard time concluding that it really is such a complex behavior, right? I mean, you would try to be a little bit more parsimonious. Like I don't think you want anywhere near as many parameters as you have data points. You probably want much fewer parameters than data points. Because I mean, I've seen this time and again. People like make some method, they train it on some tests, on some data that's, you know, maybe not really different from the training data, and they get some results, and they think, oh, wow, it's actually, I've actually done this. Like you think, oh, wow, I have a method, and then you test it on something completely new, and it has crappy performance, right? Overfitting. I'm pretty confident that you would need to roll this out, because look at the number, this is 20 neurons, and look at how many points it is. It's something like 25 points or something. So it's a little bit of just too many parameters for just such a small data set. But I mean, you're welcome to go and argue your point with Arnett. I mean, it's probably worth at least some partial credit, right? All right. Any other questions?